The specific heat capacity is the energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it can be measured in joules per gram degree Celsius or in calories per gram degree Celsius. If you take a look at this chart, there are many common substances on it. So I want you to take a look and find the highest number on the chart and the lowest number on the chart. And pause the video for a second and take a look. You'll notice that the highest number on the chart is water. And this is the highest specific heat, and it's the hardest to change the temperature. It takes the most energy to change water over almost any other substance. And the human body's pretty darn close at 3.5 joules per gram degree Celsius because it's mostly full of water too. Things that are metals like copper, steel, silver, and mercury have low specific heats because they're all metals, and metals have a sea of free-flowing electrons, and so it's really easy to change their temperature because those free-flowing electrons allow the temperature to change really easily. So there's an equation that relates the mass of an object, the change in temperature in the object, so we know that it's transferring energy, and the specific heat capacity. So it's Q equals M times delta T times Cp. So the Cp stands for capacity, delta T is change in temperature, M is mass. So the units we use for heat are joules, represented by a capital J. Mass is in grams, with lowercase g. Temperature is in Celsius, degrees Celsius. Specific heat has kind of a funky unit, but once you start doing these problems, you'll understand why. It's in joules per gram degree Celsius. So we're going to calculate the heat change for 500 grams of iron as it cools down from 100 degrees to 22 degrees Celsius. So Q equals M, which is 500. I'm going to go ahead and include all my significant figures, times delta T, which is 100 degrees minus 22 degrees Celsius, times the specific heat of iron, which is up here in our chart. Iron's right there. It's 0.444 joules per gram degree Celsius. So you can go ahead and plug that into your calculator. Just multiply all those numbers together, and you get 17,300 joules. So it's cooling off, so that's how much energy is released. Okay, now let's do the same thing for water. So remember that for water, milliliters and grams are the exact same thing. That only works for water, though. If it's some other substance, you have to look at its density and do a conversion. Water is 4.18 joules per gram degree Celsius. You'll have that memorized after not too long because we use it all the time. And you get 163,000 joules. So even though we had the same amount of material in both of these substances, the amount of energy released from the water as it cooled off was much greater because it has a much greater specific heat. On the back of your notes, you'll see a temperature graph of the average temperatures in Kansas City and the average temperatures in San Francisco, California. So what I want you to do is look at the difference between these two graphs and their average temperatures over this time period. So Kansas City is a fairly landlocked area. In all directions, we have a few rivers, but that's really it. San Francisco, on the other hand, is surrounded by water. So here's a map of San Francisco, California. You'll notice on your graph it's extremely temperate there. The average highs and lows don't change much throughout the whole entire year. But you can see why. Look at all of this water that surrounds San Francisco. that water makes it really difficult to change the temperature in that area because water is extremely resistant to changes in temperature.